Every story has to start somewhere.
And this one starts with the ground rushing up to meet you. Drop a stone. It falls. You already knew that. You have known it your whole life, in the way you know that the sun rises and the seasons turn. It is so ordinary that it barely registers as a fact worth examining. And that, as it turns out, is exactly the problem. For most of human history, things fell because that was simply what things did. Rocks belonged to the earth. Fire belonged to the sky. Objects moved toward their natural place, and that was the beginning and end of the explanation. The ancient Greek philosopher Aristotle codified this intuition into a tidy system. Heavy things, he said, fall faster than light ones. The universe sorted itself by nature, by essence, by what a thing fundamentally was. It felt right. It felt complete. And for nearly 2,000 years, almost no one pushed back. But here is the thing about a question you never ask. It does not go away. It waits. Somewhere in that long silence, the waiting ended. Thinkers began to notice that the tidy system had cracks. A feather and a hammer did not fall the way Aristotle predicted. Not exactly, not always. The world kept offering small, stubborn contradictions, and a few restless minds began to wonder whether falling was a behavior to be described or a mystery to be understood. Those are very different ambitions. The shift was slow. It was not a single thunderclap moment, despite what the legends suggest. The story of an apple striking a famous head is almost certainly embellished, and yet it persists, because it captures something emotionally true. The universe is always dropping things on us. The question is whether we bother to look up and wonder why. What early investigators were really doing, even before they had the mathematics to prove it, was separating observation from assumption. Yes, things fall. But how fast? At what rate does the speed change? Does the weight of the object matter, or does it not? These seem like simple questions. They are not. They require you to distrust your own eyes, to design careful tests, to measure rather than merely watch. That discipline, humble and painstaking, would eventually crack open the sky. It would reveal that the moon is not sitting still above us, but is, in a very real sense, falling too, falling constantly, curving endlessly around the earth, missing the ground because the ground keeps curving away beneath it. Gravity, it turns out, is not just the reason your coffee stays in your cup. It is the reason the solar system holds its shape. We begin here, then, at the surface of things, with a stone in the hand, a question in the mind, and the slow, magnificent realization that the most familiar force in the universe is also the least understood.
And so we pick up that stone, and we let it fall. Isaac Newton did not watch an apple strike his head and suddenly invent physics. That story is a comfortable myth. What Newton actually did was something far more remarkable. He sat with a question that everyone else had stopped asking. Why does anything fall at all? And he refused to let it go. What he arrived at, after years of mathematics and solitary thought, was a law so clean it feels almost like cheating. Every object in the universe pulls on every other object. The strength of that pull depends on how massive the two objects are, and it weakens as the distance between them grows. Double the distance, and the force drops to a quarter of what it was. That relationship, precise and universal, is the same whether you are talking about a stone dropped from a window in Cambridge or the moon held in its orbit around the Earth. That last part was the breathtaking leap. Newton looked up at the moon and recognized it as a falling object. It is simply falling sideways fast enough that the ground keeps curving away. The same invisible thread that tugs your coffee toward the table also holds the solar system together. For more than 200 years, that was enough. Newton's law predicted the tides, explained the orbits of planets, and guided the calculations of astronomers with stunning accuracy. Gravity was a force, invisible and instantaneous, reaching across empty space like a hand through a curtain. Then came Einstein. And he did what the best scientists always do. He noticed something that did not quite fit. Newton's gravity acted instantly across any distance, which troubled Einstein deeply. Nothing, Einstein believed, could travel faster than light. So how could the sun's gravitational grip reach the Earth the very moment the sun moved? It could not. Something in the picture was wrong. And if the picture was wrong, the whole frame needed replacing. Einstein's answer was so strange and so beautiful that it takes a moment to let it settle. Gravity is not a force at all. It is a shape. Space and time are not a fixed, empty stage on which the universe performs. They are a fabric, flexible and responsive, and massive objects bend that fabric the way a bowling ball bends a stretched rubber sheet. The Earth does not pull the moon toward it. The Earth curves the space around it, and the moon simply follows the straightest path available through that curved space. What we feel as gravity is the geometry of the universe guiding us along. Place a marble on that rubber sheet near the bowling ball and watch it spiral inward. That spiral is not caused by a force reaching out and grabbing the marble. It is caused by the shape of the surface itself. We are all just marbles, rolling through a universe that is forever curving beneath us. Newton gave us the rules. Einstein gave us the reason. And the universe, it turns out, is far more supple than any of us imagined. And if we are marbles rolling through curved space, then consider what happens when the curves grow steep enough to swallow everything. Out at the edge of what we can see, gravity is no longer a gentle nudge between two objects. It is architecture. It is the force that gathered loose hydrogen in the early universe and squeezed it into the first stars. Those stars burned and died and scattered their dust, and gravity pulled that dust together again, patiently, over billions of years, building galaxies the way a river builds a delta, slowly, without intention, with absolute certainty. A galaxy is not simply a collection of stars. It is a gravitational community, hundreds of billions of stars, bound to one another across distances so vast that light itself takes tens of thousands of years to cross them. And yet they hold. They wheel together through space like a slow, silent storm. But here is where things grow strange. When astronomers measure how fast the outer edges of galaxies spin, the numbers do not add up. There is not enough visible matter to generate the gravity needed to keep those outer stars from flying off into the dark. Something else is holding them, something we cannot see, cannot touch, cannot directly detect. We call it dark matter, which is really just a name for our ignorance, a placeholder for a mystery that sits at the heart of everything we think we understand. Gravity is pointing at something we have not yet found. And then there is light, light which has no mass and yet which bends. When a galaxy cluster sits between us and something more distant, its gravity warps the space around it so severely that light curves around it like water around a stone. We see the background object stretched into arcs, sometimes multiplied into several ghost images floating around the cluster's edge. We call this gravitational lensing. Einstein predicted it. The universe delivers it, every night, in every direction we point our telescopes. Black holes are gravity's most extreme statement. A star massive enough, at the end of its life, collapses under its own weight past any point of return. The curve in space-time becomes a cliff. Light itself cannot climb back out. Time, near the edge of a black hole, slows to something almost unrecognizable. And at the center, our equations simply stop working. They return infinities, which is physics admitting it has reached the edge of its own language. And yet, Even across all of this, the dark matter, the lensing, the black holes, the vast filaments of galaxies stretching across the observable universe like threads in a cosmic web, it is all one force. The same pull that holds your feet to the ground, the same geometry that kept the planets circling the sun while life slowly learned to breathe. Gravity does not care how far things are from each other. It reaches. It always reaches. And in a universe this large, that is the closest thing to a miracle that physics knows how to offer.